Hey, I think I'd show a little trick I came across playing around with hyperbolic tan, uh, hyperbolic trig functions. It's a similar trick that comes up when you're trying to do integrals with integrals and derivatives of inverse trigonometric functions. Um, like, but because you have a classic identity of the derivative of an inverse function equals 1 over the inverse, 1 over the derivative of the function itself evaluated on the inverse function. And that ends up meaning you have things like 1 over cosine of arc sine of x. If you want to find, for example, the derivative of arc sine, and then you end up feeling a little stumped from there because you wonder what in the world is the cosine of arc sine. The nice way to solve that is you just draw a triangle, right angled, and arc sine of x, that's an angle. And we can construct this triangle to make that angle arc sine of x. The most straightforward way I know is to make that height x, make the hypotenuse 1. So the sine of this angle is indeed x over 1 equals x. So sine of x is, sine of the angle arc sine x indeed gives you x. You can do the same sort of shenanigans with hyperbolic trig functions. It took me a while to learn this, and it only became more helpful when I was dealing with things in special relativity, space-time diagrams, and I want to calculate, rapidities or boost velocities, or and so on. It also comes up in doing integrals with hyperbolic trig functions and all that. But you do basically the same deal, but instead of saying, okay, with this triangle, I can find what the cosine of arc sine of x is, because I know a squared plus b squared is c squared. I know the Pythagorean theorem. And that tells me x squared, tells me 1 squared minus x squared has to be this third 1 squared. So I just found that that final length is square root of 1 minus x squared. And that means cosine of arc sine x, that is going to be 1 minus x squared, square root all over 1. And there we go, 1 minus x squared. That lets us solve the original problem. We know what the derivative of arc sine is now. And of course you have to assume suitable domain of x and all the other uninteresting, annoying things. I'm going to ignore that subtlety for now. Apologies for the roundabout way of getting to this, but this is a classic way to evaluate trig functions on inverse trig functions. You can do the same thing with hyperbolic trig functions. Okay, let's start with a nice invertible function, which would be sinh of x. which is e to the x minus e to the negative x all over 2. Say we're curious about the derivative of the inverse sinh function. Well, as a general rule, remember, this derivative of the inverse function is 1 over the derivative of the function itself evaluated on the inverse function. So that means we want to find 1 over what is the derivative of sinh? That is cosh of x. It's very easy to show. So we have cosh acting on inverse sinh of x. And now you wonder, do I really have to go through all the logarithms of arc sinh x and do the exponentials and add them up and factor? No. No, you can reproduce exactly the same thing with the triangles. And that is because of the hyperbolic Pythagorean identity. Cosh squared minus sinh squared is 1. So, I'm drawing a little pretend mnemonic triangle to think about this. I wouldn't take it nearly as literally as usual one in trigonometry. Here is our angle, arc sinh of x, and we want to find what is cosh of that. Well, arc sinh x, I'm going to naively throw an x there, a 1 there, so that sinh of x, or I guess I'll say of theta, it's theta equals x over 1 equals x. This is the mnemonic. I haven't proved this, but it works out. I ought to prove it, but nah. Here's your mnemonic. And with that mnemonic, we're of course going to do the same thing as we did before. We're going to solve for this side. Well, we know cosh squared of theta minus sinh squared of theta equals 1. Well, sinh theta, we just said, is x, because this is the inverse hyperbolic sinh. So that means this is x squared. So we have cosh squared theta equals 1 plus x squared. So cosh theta equals root 1 plus x squared. And what do you look at that? Look back at what we wanted to evaluate. The inverse hyperbolic sinh. What is its derivative? We needed this cosh of an arc sinh, and we've just evaluated it. Feel free to use this mnemonic for whatever. I'm sure other people have nice proofs of this, but this is nice for integration bees if you want to get a little mnemonic to evaluate those integrals without as much thought. Thank you.